Okay, so today we're starting on the second part of the course, which is all about analyzing the stresses that occur within beams. So a reasonable place to start is just by defining what's a beam. So a beam is any structure that is loaded predominantly perpendicularly to its length. So a lot of situations we have beams that sort of look like this, where we've got some supports here, and then the predominant loadings are oriented again perpendicular to the beam's length, right? But they don't have to be horizontal like bridges or walkways or the structural members in those. For example, if we have a signpost, maybe that's attached to the ground, and there's the sign on the signpost, or maybe it's a light standard or a traffic light pole, and the wind's blowing and we have a force oriented like that, right? The pole, or the post in this case, counts as a beam because the loading is predominantly perpendicular to the object's length. So again, in this section of the course, it's all about how do we analyze stresses in beams. So let's just take a beam, a horizontal one maybe, and let's do a section cut through the beam and look at what the internal loading situation looks like. So I'm just gonna flip to a new page here to do that. So here's our example beam here, and we'll just do what's called a simply supported beam, which has a pin at one end and a roller at the other end, and let's just throw on a force here. So if this is point A over here, then this support reaction is AY, and if this is point B, then this support reaction is BY. And then if we were to take a section cut through the beam, let's just say right here, then looking at the right hand side here, we would have our force By, and then to hold this in equilibrium, we need some of the forces in the x direction equals 0. So there's no forces in the x direction here. So our internal normal force here is 0, right? There's no internal normal force. So let's just erase that for now to get it out of the way. And that's the case in a lot of beams, but not necessarily all beams. We'll see some beams that have normal forces in them when we start doing the combined loading work, but most of the beams that we'll deal with, at least at the start, won't have an internal normal force because there won't be any loadings in the horizontal direction or along the length of the beam. So we also have to have, for static equilibrium, some of the forces in the y direction equals 0, which means that we need an internal shear force V there. And then about any point in this small section that I've drawn, the sum of the moments need to be equal to 0. So here we need an internal moment M that would end up acting in that direction. So for beams, the primary internal forces are our internal shear force V and our internal moment M. Now, as we know, an internal shear force gives rise to a shear stress. And as we will see in a couple of lectures, an internal moment gives rise to a normal stress. And because those stresses, the shear stress arising from an internal shear force and a normal stress arising from an internal moment, those stresses are proportional to those internal forces. So in cases where we're looking for the maximum stress, either the maximum shear stress within a beam or the maximum normal stress due to an internal moment within a beam, what we want to know is, first of all, what is the maximum internal shear force along the length of the beam, and what's the maximum internal moment along the length of the beam. So that's what today's lecture is going to focus on, is being able to find where and what the values are of the maximum value of internal shear force and the maximum value of internal moment. Okay, so let me just write some notes about what I just said there. So we said because our internal, or let's erase shear force, because the shear stress is proportional to the internal shear force, and the normal stress, as we'll see, is proportional to internal moment, to find or calculate tau max and sigma max, we need V max and M max, right? And we get these from what are called shear and moment diagrams. Shear and moment diagrams. Okay. So in this lecture, I'm going to teach you how to draw shear and moment diagrams using what is called the method of sections. Okay. So what we're going to do here, first of all, is I'm going to put up the first sort of example, and I'm going to teach you how to do this through doing the example. But first of all, I want to put up the example beam, and then I'm going to draw what the shear and moment diagrams look like and talk about what those mean first, and then I'll teach you how to draw them using the method of sections, okay? So here's what our beam is going to look like. Okay, so we've got a simply supported beam here, roller at that end, pin at that end, and we're going to have a point load right in the center that has a magnitude of 15 kilonewtons, and then a distributed load over this half, and the value of the distributed load is going to be 5 kilonewtons per meter. And then we're also going to have a point moment at this end of the beam, and the point moment's value is going to be 80 kilonewton meters. And in terms of distances, to the center of the beam from the roller is going to be 5 meters, and from the 15 kilonewton load to the pin is also going to be 5 meters. So that's the beam that we have. Now, what I'm going to do is I'm just going to draw on the right on the support reactions here. So if we made this a free body diagram and did some of the moments about any point and some of the forces in the y direction, then these are the support reactions that we'd get. So this support reaction here would be 5.75 kilonewtons, and this support reaction here, By, would be 34.25 kilonewtons. Okay, so when we draw shear and moment diagrams, we always do a sort of a 3-tier stack. So it's always free body diagram at the top, shear diagram directly below that, and moment diagram directly below the shear diagram. And as we learn how to draw these, you'll get to see why we set them up that way. So I'm going to set the axes up for my shear diagram here. Okay. Here we go. So I'm going to measure my shear in units of kilonewtons. And what the shear diagram for this beam looks like is something like this. And it's not necessarily to scale here, but that's the general shape of it. This has a value of 5.75. This here has a value of minus 9.25, and this point over here has a value of minus 34.25. And I always like to do some shading on my shear and moment diagrams to make it clear what side of the axes, the horizontal x-axis, the shear is on. So I always find it's helpful to draw some construction lines too, just relating where the points of interest are on the shear diagram relative to the loads of interest on the free body diagram. So I draw one sort of construction line there and one sort of construction line there. So now I'm going to stack my moment diagram below this, and the moment diagram is going to be in kilonewton meters. Go. Okay, and I'm going to continue those construction lines down like this. Okay, there we go. And my moment diagram looks like this for this beam. Okay, and that has a value of 108.75 kilonewton meters. This has a value of 80. Okay, do some shading on that one too. Okay. So those are what the shear and moment diagrams look like for this beam. Now, before I teach you how to draw these, I just want to talk about what they mean first of all. So let's start with the shear diagram. This horizontal axis along here, that represents the position along the beam's length. So that axis is really length L there. And on the Y scale, we've got what the value of internal shear within this beam is at every length position L. So, for example, if we look at this position right there where I've drawn my section cut, if I were to draw a section cut of the beam at that point there, I could look at my shear diagram and quickly know that let me get my blue pen there. The internal shear is 5.75. It has a value of 5.75, right? Because we trace that position down to the shear diagram and read off the corresponding value, which is positive 5.75. And we'll talk about this in a minute, but a positive value of shear corresponds to an internal shear in that direction. Okay, and then you could trace it down farther, right? And if we had an exact length position there, we could figure out what the value of our internal moment here was too, right? So we'd have an M there. If we take a point that's a little better defined, let's say a spot that is, let's say, right in the center of the beam here. Okay, then we know at that location there, trace it down. So here we've got an undefined value of shear, right? The line's vertical, so the shear force here is undefined right at that position, so we won't show one. And then we've got an internal moment here that is 108.75. 108.75. Okay. And then same sort of thing, if we were to take a section cut through the beam here, we could use our shear diagram to trace that line down, figure out what the internal shear is at that location by reading off this value, figure out what the internal moment is by reading off the value at that point on the curve. So we get the values of internal shear and internal moment at any length position along the beam that we want. Now, as I said previously, the thing that we're usually interested in is, for example, what's the maximum shear stress? And the location of maximum shear stress corresponds to the point where we experience the maximum internal shear force. So very quickly from the shear diagram, we can see that the maximum internal shear force, which is the absolute maximum value of shear, is this point right down there that has a value of minus 34.25, and that occurs right at our right-hand support, pin support. And if we wanted to know what the maximum internal moment is, we can actually very easily identify that. So it occurs right in the center of the beam, and the value is 108.75. So now let's talk a little bit about sign convention. So as you can see from the shear diagram in particular, we've got values of shear that are both positive and negative. So what's a positive internal shear and what's a negative internal shear? And that can happen for the moment diagram. We've only got positive internal moments here, but you can have a moment diagram where you have negative internal moments or positive and negative internal moments. So we need to have a sign convention to tell us what is a positive internal shear force and what is a positive internal moment. Okay, so this is the sign convention for positive V and positive M. Okay, so if we look at a little section cut here, okay, a positive internal shear force is defined as an internal shear force that would act to rotate this section clockwise. Okay, so the shear force that would act to rotate this section clockwise is one that would act downwards. So that's a positive internal shear force. Okay, so this positive V acts to rotate our section clockwise. Okay. Now, a positive internal moment, if we do the same sort of thing where we just draw some random section cut here, a positive internal moment is defined as an internal moment that would act to bend the beam into sort of a smiley face configuration, or more technically, puts the top of the beam in compression. So that's an internal moment that acts like this. So positive M puts top of beam in compression. Okay. The top of the beam is in compression when the beam bends into sort of a smiley face configuration. Beam into smiley face. So if you imagine thinking about taking a ruler, right, and you use your hands to bend the ruler like that, then you know that the ruler is going to deflect like this. So that sort of smiley face configuration, that's a positive moment. And then the opposite would be true for a moment that's acting to bend the beam the other way. Okay. So now that we've got the sign convention down, let's flip to a new page and we'll redraw our beam, and then I'll show you how to use the method of sections to draw those shear and moment diagrams. Okay, so our beam looked like this here. So we've got 15 kilonewtons in the middle here, and then we had 5 kilonewtons per meter there, and we've got our point moment of 80 kilonewton meters there, and then we've got our 5 meter length and 5 meter length to the other support reaction. And I'm going to call this support reaction AY here, and this support reaction BY here. So there we go. We've got the free body diagram of our beam now. So the first step in doing the shear and moment diagrams is always first, so that you save the space, set up the axes for your shear and moment diagrams below the free body diagram, even before you figure out your support reactions, because you want to reserve that space here. So we're going to do our shear diagram in units of kilonewtons because all of our loads are in kilonewtons, so that makes sense. So our vertical axis for values of shear here, and our horizontal axis representing length along the beam, and then our moment diagram we'll do in units of kilonewton meters, and our vertical axis. And then usually you don't know whether your moment diagram is going to have positive or negative moments in it, so I always just like to draw my horizontal axis in the center of that vertical axis there, and then fill in your construction lines here to help you do the drawings. So line straight down to be able to relate on your shear and moment diagrams the position of that 15 kilonewton point load there, and then another vertical line down to relate where the end of the beam is, or support reaction BY, to your shear and moment diagrams. So there we go. So the first step when you're doing the method of sections is to find support reactions first. So find support reactions. Okay. So the sensible thing to, and I know you already know how to do this, but sometimes it doesn't hurt just to have another example or see this done again. So to find support reactions, it makes sense to do a sum of the moments, because sum of the forces in the y direction, you'd end up with two unknowns in that equation. So you can do sum of the moments about any point on the beam that you want. And just to illustrate an important point about point moments here, let's do the sum of the moments about point B. So, oops, don't want highlighter. We don't want that either. What is that? Oh, that's the magnifier. How do we get rid of the magnifier? There we go. Okay. So what were we doing? Sum of the moments about point B has to be equal to 0. Okay, so let's go counterclockwise as positive. So in terms of counterclockwise moments, we've got that 5 kilonewton per meter distributed load. So we want to take the resultant of that distributed load, which is the area within it. So we've got 5 times 5, and I'm working in units of kilonewtons for force here. And then the moment arm of the resultant with respect to point B. So that's half of that 5 meter distance. So we've got 2.5 meters there. And then we've also got the 15 kilonewton point load. So we've got 15 with a moment arm of 5. And then in the opposite direction, we have AY. So we've got plus or minus AY, because that's in the other direction, multiplied by 10. And then we've got the point moment. Now, don't forget when you're doing a sum of the moments equations, you include point moments just as they are, right? You don't take a point moment, that 80 kilonewton meter point moment, and multiply it by 10 meters because it's 10 meters away from point B. Those point moments, you sort of consider them movable. So it creates a moment about point B of 80 kilonewton meters in what we've defined as the negative direction. So it needs to go in our equation just as minus 80 equals 0. Okay. And out of that, then, we get a value for AY, which is 5.75 kilonewtons. And then we want to do sum of the forces in the y direction is equal to 0. And that's, of course, going to give us BY. So what do we have? Upwards we have AY, which is 5.75 plus BY minus 15 minus the resultant of the 5 kilonewton per meter distributed load, which is 5 multiplied by 5, and that all has to equal 0. So BY pops out of there, and it's 34.25 kilonewtons. Okay, perfect. So let's pop those in our diagram here so we don't lose them. So this is 5.75, and this one here, just erase a little bit there, is 34.25. Okay, now I'm just going to clip everything that we have on this page like this and move it to a new page for us. So let's take this, copy. Okay, let's flip over to here, paste, perfect. Okay, so the second step when you're doing the method of sections is what we want to do now is working from our left-hand side of the beam, we want to take section cuts between every point load and within every distributed load, and then analyze the free body diagram of the left-hand portion of the beam for each of those section cuts and write equations for what the internal shear and internal moment is. So there's the second step is really, the whole process. So there's really, aside from the support reactions, there's only really one step, and that's this step. And then the third step is just to graph it based on the equations that you get. But the important thing here is that we make section cuts between each point load, and within each distributed load, and then we analyze the free body diagram of left hand portion of beam, and analyze here means apply equations of statics to determine equations for our internal shear and internal moment. Okay, so make section cuts between each point load and within each distributed load, analyze free body diagram of left-hand portion of beam, apply equations of statics to determine equations for V and M. And importantly here, when we're analyzing that left-hand portion of the beam, we always draw our internal shear and internal moment in what we've defined as the positive orientation, regardless of what their real orientation is. So we always draw V and M as positive on free body diagram of section cuts. Okay, so thinking about this second rule here, let's look at how many section cuts that we're going to have to do. So we've got two sort of point loads here. So we've got an 80 kilonewton meter point moment, and we've got a 5.75 kilonewton point load. Those both exist exactly at point A, so we can't section between them. So the next thing that we have is the 15 kilonewton point load. So we need one section cut that's somewhere between point A and that 15 kilonewton point load. And then we're going to need another section cut that's between the 15 kilonewton point load and support reaction force By. And we need another section cut that's within that distributed load. So if we take one section cut between the center and point B, that fulfills both of those requirements. So we just need two section cuts in this case. So again, let's flip to a new page here, and we'll just paste on our previous drawing. So let's take our first section cut then. So that's the section cut between support reaction force AY and our 15 kilonewton point load. And remember, we're doing the section cut and we're drawing the left-hand portion of the beam. So here's the left-hand portion of the beam for that section cut. So what have we got for forces on this? Well, we've got our support reaction force AY, which is 5.75 kilonewtons here. We've got our point moment, 80 kilonewton meters. And then we've got our internal shear force. And remember, don't think about which direction it is really in. Think about putting it in the positive direction according to the convention that we've assigned. So a positive internal shear force acts to rotate the section clockwise. So this needs to go downwards like that. And then we have an internal moment, and same deal, right? Put the moment in the positive direction according to our sign convention. So that is bending the section into a smiley face configuration. So it needs to be an internal moment that's oriented in that direction. And then again, no internal normal force necessary because some of the forces in the x direction is already equal to 0. Now, the section that we've made through the beam, right here, this section could be made anywhere between point A and that 15 kilonewton load, and the picture that I've just drawn of the section cut will look exactly the same. So we call the position of this section cut just some position L measured from the left-hand side of the beam, right? Point A. Okay, so now we apply our equations of statics. And those equations of statics are going to give us equations for V and M in terms of L. And those are the equations that we're going to use to plot the shear and moment diagrams. So first of all, if we look at the sum of the forces in the y direction is equal to 0, right? This one's pretty easy. We have 5.75 upwards. And then we have minus v downwards has to be equal to 0. So our equation here is v equals 5.75. Now, because this section cut could have been made anywhere between 0 and the center of the beam, right? This equation is good for all values of L between 0 and 5. So we have 0 is less than or equal to L, less than or equal to 5. Okay. Now, let's do sum of the moments is equal to 0 here. So sum of the moments, again, you can do a sum of the moments equation about any point that you want on the beam. I like to do it usually about the center of the section cut that I've just taken so that the moment due to the shear force is 0. So if we call this point C, let's say there, then we've got sum of the moments about point C has to be equal to 0 here, and I'm just going to take, as I usually do, the counterclockwise direction to be positive. And remember, I'm not defining here this notation indicating that the counterclockwise direction is positive. This is only for my equations of statics, right? I've said that a positive internal moment is, for the purposes of the moment diagram, is a moment that puts the top of the beam in compression or bends the beam into a smiley face. That has nothing to do with what a positive internal moment is for the equations of statics, right? So here, let's look at what we've got. So a positive internal moment. Well, my internal moment here, according to the sign convention that I've set up for my equations of statics, is a positive. So we've got plus m to start with. And then the 80 kilonewton meter moment is acting in the opposite direction. So I've got a minus 80. And then I've got a minus 5.75 from AY multiplied by a moment arm of L. Okay, and that all has to equal 0. So that gives me my equation for M. M is 5.75 L plus 80. And again, that's good from 0 to 5. Oops. Okay. So now we've got, by doing that section cut, now we've got equations for how shear and moment vary between 0 and 5 meters along the length of the beam. Okay. So the next thing we need to do is take our next section cut. So what we'll do is just flip to a new page here and paste the beam back in here like that, and draw our second section cut that we need to make, so somewhere in there. And again, you want to analyze the left-hand side of that free body diagram. So let's do that. So section cut, something like that. So in this free body diagram, what we have again is support reaction AY, so that's 5.75 kilonewtons, and then we've got our point moment, 80 kilonewton meters there. We've got the point load of 15 kilonewtons, and then we've just got a little bit of that distributed load. Okay, so that's something like that, and this has a value of 5 kilonewtons for every meter of length. And again, the total length of this section is L, measured from the left-hand side. And then we draw our internal forces, and again, just put them in the positive direction. So we've got internal shear that acts to rotate the section clockwise, internal moment that acts to put the top of the beam in compression. Okay, so same deal. Sum of the forces in the y direction has to be equal to 0 for this little section cut that we've made. So what have we got here? Taking the upwards direction as positive, working from the left-hand side of the beam over. We've got 5.75 for AY, then we've got minus 15 minus the resultant of that distributed load. So remember that this length here is 5 meters. So the distributed load, the resultant, is going to be the area within that portion of the distributed load, which is 5 multiplied by a length of L minus 5. So we've got 5 L minus 5 there. Okay, a little bit sloppy there on my 5. Okay, there we go. And then we've got also our internal shear force V's, and that's in the negative direction, equals 0. Okay. Now remember that shear force, this internal shear force, again, sign convention is different between what's defined as a positive internal shear force and what I've taken as the positive direction for my equations of statics, right? The two are not related. So that's a negative shear force there according to my sign convention, but it's actually a positive shear force according to the shear diagram and what's going to be positive and negative there. Okay, so if we clean that up a bit, then what we get out of it is our shear equals 15.75 minus 5L. Okay. Now this equation is good for values from 5 to 10 meters. Okay. And we can do the same thing with sum of the moments. So sum of the moments has to be equal to 0, and counterclockwise is positive. And again, you have to take the sum of the moments about some point. So let's choose this point here and call that point D, just because we haven't used D yet. So let's see what we've got here. So again, working from sort of left to right, we've got the 80 kilonewton meter moment first, and according to my sign convention, that's a negative in my equation of statics. Then we've got the 5.75, so that's going to be creating a negative moment too. So we've got 5.75 multiplied by the moment arm, which is L. And then in the positive direction, we've got the effect of the 15 kilonewton point moment. Now the moment arm here from point D is L minus 5. So L minus 5. And then we've got the effect as well of the 5 kilonewton per meter distributed load. So we need the resultant of that multiplied by the moment arm of that resultant relative to point D. So the resultant is 5 multiplied by L minus 5. And then the moment arm there is going to be that distance divided by 2. So we've got L minus 5 divided by 2. Okay. And then I'm just going to move this over a bit because I can see that we're going to run out of room. So let's put it there. And then we've got our point moment, our internal moment M, and that's also in the positive direction, plus M, and that all has to be equal to 0. Okay, so a few terms there to clean up, but when we do that, we get the following: minus 2.5 L squared plus 15.75 L plus 92.5. And again, this is good between values of 5 and 10. Okay, so now we've got two equations for shear, two equations for internal moment, and we can use those equations to plot our shear diagram and our moment diagram. So let's go grab a new page here. Okay, and let's pop those diagrams on again. Okay, and then I'm just going to rewrite the equations for shear and moment that we had previously. So for the first section cut that we did, we had shear was 5.75, and we had the moment was, let's see, 80 plus 5.75 L. And then for the second section, and this was both good for 0 to 5. And then for the second section cut, we had V was 15.75 minus 5L, and M was minus 2.5 L squared plus 15.75 L plus 92.5. And those equations are good from 5 to 10. Okay, so now it's time to plot. So what we do is let's work with the shear diagram first. So starting at L equals 0. Remember, our L axis is on the horizontal here. So this is our horizontal axis, L, and it's measured in meters. So between 0 and 5, the equation for shear is just 5.75. So that's just a straight line with a value of 5.75, right? So there we go. So positive 5.75 is our shear in that segment. Now for the next segment, we go down and look at our next equation right there. And here we've got 15.75 minus 5L. So that's a linear line with a negative slope. The slope is minus 5. So what we need to do is we need to determine where this line, linear line with a negative slope, starts on the y-axis. So to do that, we just want to take the value of that equation at a distance of 5. So we do evaluate the shear equation at 5 meters. So we've got 15.75 minus 5 times 5, which gives us minus 9.25. Right, so we know where we're starting from. So let's put a dot there and go here and minus 9.25. And then we've got a linear line with a negative slope. So we've got a line that's something like this. And then the value that we get to here, we can get that by evaluating what the shear is at a distance of 10 meters. So we've got 15.75 minus 5 times 10. That gives us minus 34.25. Okay, so 34.25 there. All right, and then what we do is we just connect this to 0 and connect those there, and we do some shading. There we go. Perfect. Okay, so that's all there is to it for the shear diagram. So now let's move on to the moment diagram. So again, start with the first equation here that takes us from 0 to 5 meters. And in this case, we've got a linear line with a positive slope of 5.75. So do exactly the same thing that we did with the shear diagram. Whenever you have a linear line, it's nice to know where you start and where you're going to, and then just connect them with a straight line. So evaluate M at 0, which of course just gives us 80. And then evaluate M at a distance of 5, which is 80 plus 5.75 multiplied by 5, which gives us 108.75. Okay, so let's put those on. So we start at a value of 80, and then we've got a linear line with a positive slope, and going to a value of 108.75. Okay. And then we turn to our second equation here. Now, our second equation from 5 to 10 meters, we've got a quadratic that is negative. So that's a quadratic that is upside down like that. So what you'd want to do is you'd want to solve for where the maximum is of that equation there. And then after you do that, you know whether the maximum of that equation is between 5 and 10. So you know whether the curve is going to continue up or whether it's going downwards. So if you do that, you find that the maximum of that equation occurs to the left of L equals 5. So we know that our quadratic is going downwards like that in this section of the curve. So what we need to do is we need to find out where we start from, and I've kind of just given it away that we start from 108.75, but we know we have a curving line that's downwards because we know we're in this section of the quadratic there. So we need to know where we start from and where we're going to, and then we just connect them with a curved line. Right? Or the even easier way is just to put that equation into your graphing calculator and just graph it between 5 and 10. So let's evaluate that equation at 5 and 10 and see what we get. Now I'm just going to move this all up so we don't have to open up a new page here. There we go. So we want to do m of 5, okay, and that's minus 2.5, and then we put in 5 and square that, plus 15.75 multiplied by 5 plus 92.5, and that indeed gives us 108.75. And then let's see where we get to at a value of 10 if we pop that in for L. So we've got minus 2.5, 10 squared plus 15.75, 10 plus 92.5. Okay, and that, if you keep all your decimal places, comes out to be 0. So in this section of the curve, right, we start where we left off at, and we have a curving line with a negative slope that takes us back down to 0. And do some sketching. Okay, so that's how we do our shear and moment diagrams, right? Now the third step that we left out here, which is kind of implied but I didn't write, is just after you build up the set of equations, then graph your shear and moment diagrams. So 3, graph or plot V and M diagrams. Okay. Now, usually what we're interested in doing or learning from this is what is the maximum value of internal shear and what is the maximum value of internal moment. So if we were going to write these, our maximum value of internal shear is 34.25 kilonewtons, and I'm just taking the absolute value there because a positive or negative just tells us whether that internal shear is acting upwards or downwards on the left-hand section cut that we've made, and whether it's positive or negative doesn't affect the fact that it's going to cause shear stress. It just changes the orientation of the shear stress. So if we were looking for maximum shear stress, what we'd want is the maximum absolute value of internal shear force. And then our maximum internal value of our maximum internal moment is 108.75 kilonewton meters. Okay. Okay. So let's do one more example here just to really make the process sort of solidify for you. So we'll do a beam now with a linearly increasing distributed load on it. So we've got a load that starts like that and increases in a linear fashion from one end to the other end. Okay, so there it is. Distributed load. So at this end, we'll say that the distributed load has a value of 2 kip per foot, and at this end, the value is 6 kip per foot, and that's a linear increase between. And then we have a beam length here of 18 feet, and I don't know, let's say, well, roller on one end, pin on the other end, but let's just put in the support reactions here, AY and BY. There we go. Okay, so what we want to do is draw the shear and moment diagrams to determine the maximum internal shear force and maximum internal moment. Okay, so if we write the question for the example, it would be draw V and M diagrams to determine V max and M max. Okay. So first things first, let's set up our axes for shear and moment. So we've got V. All the loads are in units of kip, so we're going to draw our shear diagram in units of kip. So Here's the axes being set up. And then our moment diagram. We've got kip and feet, so let's do this in kip feet. Okay. And same thing. Then our horizontal axis, which is length along the beam. And no points of interest in the center of the beam anywhere, so the only line that I draw would be one going down like that for the end of the beam. Okay. So now let's start by figuring out what our support reactions are. So some of the moments about point A, let's say, has to be equal to 0 for this beam, positive direction counterclockwise, which I like to take. So in the counterclockwise direction, we've got the effect of By, so By multiplied by its moment arm of 18 relative to point A, and in the other direction, we've got the distributed load. So the best thing to do with a distributed load like this is just to break it up into a rectangular section and then a triangular section. So for the rectangular section, the resultant of that is going to be the area within that rectangle, which is 2 multiplied by 18, and then the resultant is going to be located right in the center, which is a moment arm of 9. And then for the triangular portion, whenever you're dealing with a triangular distributed load like that, right, the resultant is the area within that triangle. So you're taking the area within that triangle, and that resultant there is always located at a distance of 1/3 of the base length of the triangle from the large end. So if the whole base length here is distance L, then that distance from the large end of the triangle is 1/3 of L. Okay. So what have we got? The area of the triangle, 1/2 the base, 18. The height is 6 minus 2 is 4. And the distance from point A, the resultant is located 1/3 of the base from point B, so that's 2/3 of the base from point A. 18, 6, 12, 18, so 12 feet from A would be the resultant. And then that's equal to 0. Okay, so that gives us By is equal to 42 KIP, and then we can do sum of the forces in the y direction equals 0, positive direction upwards for me. So we've got AY plus BY, which is 42, minus, again, the resultant of the rectangular portion would be 2 by 18, and then minus 1/2 base times height for the triangular portion, and that all has to equal 0. So we've got AY is equal to 30 kip there. Okay, brilliant. Now we've got our support reactions. So let's do the same old thing. Oh, actually, before we copy paste that, let's write in our support reactions so we take those with us. So we've got 30 here and 42 there. Great. Okay, now let's take the whole thing with us to the next page. Okay, copy. Okay, new page and paste. Great. Okay, so now let's think about applying the rule that we needed to apply. So we want to make a section cut between every point load and within every distributed load. So there are only 2 point loads here, the support reactions AY and BY, so we need to be between those, and we need to be within every distributed load. So we only need one section cut here. So let's just cut it right in the middle somewhere like that. Well, not exactly in the middle, but just at some variable position L, right? Because we want equations that are in terms of L. So you don't want to cut at a specific location. So maybe I'll just move that to illustrate that we're not cutting straight in the center. We're just cutting somewhere at a variable position L. So let's draw what the beam looks like here with its section cut. Okay, and then what do we have for loads on that little section? We've got 30 kip there, and this has a value of 2, and then it increases linearly to some value where we've got cut off there. So at this end we've got 2 kip per foot, and at this end we've just got some height, let's say h there. All right, now we've got our internal shear force and our internal moment. So again, just throw these on in the positive direction according to our convention. So positive internal shear force acts to rotate the section clockwise, and positive internal moment acts to bend the beam or the section into a smiley face. So there are our directions for those. Okay, so now it's just a case of putting on the fact that this is some length L, and then applying our equations of statics. So let's do first, sum of the forces in the y direction has to be equal to 0. Positive is upwards here. Okay, so what do we have in the positive direction? We've just got our 30, and then we've got subtract. All right, let's look at breaking this up into 2 segments here again, that distributed load. So we've got the rectangular portion first, and that is going to be, as a resultant, 2 multiplied by L. And then for the triangular portion here, we've got 1/2 base times height. Okay. Now, we don't want to go throwing a variable of h in our equation here, really, because that's just going to add an extra unknown that we're not going to be able to graph. So what we can do is we can replace that variable h and write it in terms of the variables, or not the variables, but the starting and end points of the distributed load. So for example, we know that if we draw the triangular portion of the full distributed load here, okay, we know that this side here is 0, and this side here is 4 kip per foot, okay, and this whole base length is L here. And we've done our section cut at some position here, and we've called this value h. Now, the small triangle here and the big triangle share this same angle here, so the ratio of the, this should not be L there. That full base length, we know what that is. That's 18. Let's put that in red because we usually do distances in red. 18, and the small portion of the base is L, right? So this is L right here. That's our variable up there. And the 18 represents the full length here of that base, okay? All right, let's just take this and move that over here to avoid confusion. So that's 18 feet. Okay, so we can do a ratio between the height and the base of those triangles to be able to write h in terms of other things. So we know that, for example, do this up here. We know that h divided by L has to be equal to 4 divided by 18. So h is 2 over 9L, right? So then let's put this in our equation down here. Let's continue that. So the resultant of the triangular portion of the distributed load, that portion there, the resultant 1/2 base times height, we've got the 1/2 base now, and we know the height of that, so h here again is just the height relative to the top of that rectangular portion of the distributed load, and its value is 2/9 L. So we've got 2 over 9L here. Okay, and then what do we have for forces in the y direction remaining? So we've just got our internal shear force V, and that's in the negative direction, minus V equals 0. So tidying that up a bit gives us an equation for shear of minus 0.11 L squared minus 2L plus 30. And that's good for any position within the beam. So this is good all the way from 0 to 18 feet. Okay. All right, so now we have to do sum of the moments is equal to 0 for this section cut. So again, I like to choose the center of the section cut that I've made so that I don't have my shear force in the equation. It's got a moment arm of 0, so it cancels out. So this is point C there. So I'm going to do the sum of the moments about point C is equal to 0. Positive direction counterclockwise there. So let's see what we have in the, starting with the 30 kip load. That's a negative internal moment according to, or a negative moment according to the system that I've set up for statics here. So we've got minus 30 multiplied by a distance of L away from point C. And then we've got positive. Now the rectangular portion of that distributed load, its resultant is 2 by L. And its moment arm is L divided by 2. And then we've got the triangular portion of the distributed load. So its resultant is 1/2 of the base length times the height, which we said was 2 over 9L. And then we know relative to point C, it's going to be located 1/3 of the base of that triangle away. So that is 1/3 of L away from point C. And then also contributing a positive moment is the internal moment. So we've got plus m equals 0, right? Okay, so let's tidy that up a bit, and what do we get out of that? We've got minus 0.037 L cubed minus L squared plus 30L. Okay, and again 0 to 18. Okay, so let's go to the next page and graph those values there. Okay, so let's paste that there, and then let's just write our equations again. So we've got a shear equation is minus 0.11 L squared minus 2L plus 30, and our equation for moment is minus 0.037 L cubed minus L squared plus 30L. Okay, so let's start with our shear diagram first. Okay, so the way you want to start here is just by evaluating what shear is first so always do the endpoints first, right? That's a good way to start. So we've just got one equation that covers the full length, so let's evaluate our two endpoints. So let's figure out what V of 0 is and what V of 18 is. So we just plug those in there. So we can see quickly that that's 30, and then we do the math on this to figure out what the other one is. Minus 2 times 18 plus 30, right? And that gives us minus 42, okay? So thinking about this equation, again for shear, let's look at it. It's a quadratic that's negative, so again it's going to be sort of a mountain like that, and best thing to do is just figure out where the maximum is. The easiest thing is just to graph it with your graphing calculator, but if you don't have a graphing calculator, then you can figure out where the maximum point is by let's say taking the derivative and setting that equal to 0 and then solving for L. In which case, again, you find out that we're in this portion of the curve here over the range 0 to 18. So we know we've got something with a negative slope that's curving downward. So we start from positive 30, and we go to minus 42, and we've got a curving line with a negative slope. So this is right some point over here, so we know where we're starting and we know where we're finishing. So it's something like that. Okay, again, not necessarily drawn to scale here. Okay, there we go. Now, next, we've got our moment diagram. So the moment diagram is a cubic, so it really could look like anything. So easiest way to do it, graphing calculator. And barring that, you know, take the derivative, find where the roots are, blah, 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 blah. So once you figure out what the general shape looks like of it, let's figure out where we start and where we end. So the moment at 0 is, well, that's an easy one, 0. And the moment at 18 is minus 0.037, 18 cubed minus 18 squared plus 30 times 18. Okay, and if you do that and keep, again, if you've kept all your decimal places, you find that it comes out to 0 exactly. So we start at 0 and we end at 0, and we've got a curvy thing in between. So that ends up looking something like this. Okay, if you graph that. All right, now what we need to do here is we need to figure out what the maximum value of this curve is. So if we want to do that, so we can take the derivative of our equation for m, set that equal to 0 to find out where the roots are. Then take the root that's appropriate because there's only one maxima in here, and put that back into our equation for m to figure out what the value is. So we want to do dm by dl, okay, here, which gives us minus 0.037 multiplied by 3, l squared, minus 2l plus 30, and then we set that equal to 0. Solve for the values of L. So one of the roots there comes out to be 9.73 feet, and the other root is outside of the range 0 to 18. So we can ignore that one. It's a real root of the equation, but it's not a real solution to the problem because it physically doesn't make sense. So now what we do is we evaluate the moment at 9.73. Okay, so we've got minus 0.037, 9.73 squared minus 9.73 squared. Oops, that should be a cube back there. Let's put that in, cube. And then we've got plus 30 times 9.73. Okay, and we'll do some shifting things around here to create some room for ourselves. Okay, come on up, come on up. Okay, and come on up. Perfect. So we can even move this a bit to the left and save a line here if I can ever get it outlined. Okay, there we go. So this comes out to be 163.1, and that's in units of kip feet. Okay, so this value here is 163.1, and it is located at a position of 9.73 feet. So from the diagrams now, what we can see is that our maximum shear, right, is minus 42 or 42 if we take the absolute value, 42 kip, and our maximum internal moment, Mmax, is 163.1 kip feet. Okay. Now, interestingly, if you look at the position here where that shear diagram crosses 0, you will see that this is 9.73 there. And that's not an accident. So the location where V is 0 is located, or gives you the position where the moment is maximum. And we're going to see why that's true in the next lecture when we look at how we graph shear and moment diagrams using the graphical method instead.